Thank you. Thank you so much. Let's thank our speaker again. And welcome our next speaker, Jeff Stewart from Orion Space Solutions, to talk about inferring correlated neutral and electron densities from ensemble data assimilation. All right. Our next speaker is Dong Wu from NASA Goddard Space Flight Center. Is this an online presentation?
Yeah. I'd like to share my presentation if possible to.
Yes, you can go ahead and share.
Okay, let me share. You see my screen?
Yes, we can see it, but it's not in presentation mode.
Yeah, I will generate it to do this way. Okay.
Perfect.
Okay, let me start from the beginning. All right, yeah. Sorry, I couldn't be there due to the conflict in my schedule. I like to acknowledge this work is a collaboration between NASA and Air Force Institute of Technology. Just a quick look, quick outline for this. We're very interested in this superstorm because this is very rare events. You don't see this in 20 years. And kind of a two solar cycle. And we are very interested in the processes behind this storm. The RO and occultation technique can give you the insight of ionosphere, how this change, not just the total column integration. So you heard so many from previous talk that the sampling is not enough. Actually, ionosphere is very, very data hungry. And we wish for this storm, typically I like to have hourly and at least 5 degree, but I don't have that one. So I'm going to show you the observation from 2 hourly was a zonal mean, and 4 hourly, this is in the E region, and F region, we have to course it by 4 hourly, and for the map on Mosaic, I have to do even wider time band. But you can get a picture that we will never see this storm before. And I will give some summary and the lesson learned from this storm. For the this event compared to the previous we call the Halloween events in 23, this one it's both has this we call the let me using this pen who are maybe it can help you can see my cursor better. So this is a very strong, that's what we call superstorm. Mine is 400 nanotesla reverse in this, and everything happens in few hours. Then this is very rapid. I will show you the movie and start recovering later on. We really want to know what's happening here in addition to those slow recovering phase. Different from the previous storm that they have 2 punches to the Earth, magnetosphere and ionosphere. And this one, they only have 1 punches, but a very long tail. So we have data. This is what we have the data right now. For this study, I use all the cosmic data and also NASA CSDA SPIRE data. In the E region, you have this number roughly. And I add Fengyun data for this. F region, you have much fewer sampling. And so that's why you have to get a coarser. I hope to get a more this data. Unlikely, it look like we won't have this data from NASA CSDA and also NOAA data. But still better than everything you saw in the past. This is from last events. We only have a CHAMP and maybe SARC. And so for this snapshot, you can see the paper. We can only use an orbit, 3 orbit to see how the enhancement was above satellite altitude. Now we have a lot of this there. Can we do better job? So you can see this map in May. I want to point this out again. You see this a hole in due to the Ukraine's Russian war, and this is actually due to SPIRE that they pre-qualify. I think the QC out in the level 1 processing. So none of the data go through this, and that's basically a data hole. And I think Planet IQ did a similar step on this. So I would, this is one of later on, I will make a recommendation. So you won't see data, any observation during this storm on this spot, very, very few. And I would like to use this one to show you the movie, how they run. So let me see, I can play this movie. Somehow I couldn't do this with this blocking in my, okay. So I will skip this movie, but a nutshell is that there's a synopse scale and mesoscale development, the TID happened here and also in Europe. This is what happens in the, maybe I can do this way. So this is okay, yeah. So this is a synopse scale and a mesoscale region that we hope to, using the GPS data, to fill in that few hours events, including this vast no data zone. This time we feel quite a bit of it, but still not ideal to understand what the process is going on here. So the data we have, we had developed the two algorithms. Essentially, they're the same, but the technique for the E region, they're using RO data. We call the bottom-up method. They run all the way from D region to the about 120 kilometer, and also the other one is using pod data. Using this link, this data require absolute slant pass, slant TEC. This one's only relative to TEC. You can do this retrieval. So this one is similar to the onion peeling, except we're using the this optimization method. This equation, if you look at that, is a vector inversion, very similar to the data simulation technique, except in the data simulation technique, their a priori is from model. In this case, I'm using single profile to start with, and just let as TEC to change all this profile. And we validate this one. We did a very good comparison with NCAR data, UCAR retrieval on peeling. We need to be cautious that both of this, assuming the spherical symmetric, so symmetry. So this lower part of our ionosphere is vulnerable to the homogeneity. So that, but I want to point out this one is can be extended to tomographic retrieval. If we have to do the 2D along the curtain, we can do that. And I think it's doable, but that will be a different talk. For F region, like I said, we cannot afford 2 hourly. We're going to have a lot of data. I will just show you Spire only versus Spire plus Fengyun. You will see the differences in sampling. In this time series, this is no mean at about 290 kilometer. You can see as the storm start at this hour and suddenly depletion in the northern hemisphere here. There's a lot of spotty sampling here. I think it's due to sampling after you add Fengyun. You can see much smooth, nice coverage without much fluctuation. When you have missing data or missing longitude, you tend to generate the artificial fluctuation. So you can see this northern hemisphere has a much wider response, longer and deeper into the tropics, where the southern hemisphere has very narrow and not very extended. And the post the initial shock, and there's kind of weakening in the subtropical. This is what they call the equatorial anomaly, EIA, and reduced northern hemisphere, but a strengthening in the southern hemisphere. So this is a very obvious from both data set. Even the sampling is not right, and that's asymmetry due to the hemisphere in the F region, daytime, and when you go to nighttime, you sort of see a similar thing, but value is much lower at this altitude, but you do see this a little bit depletion of the northern hemisphere, and you don't see much because southern hemisphere similar thing. You see the enhancement in this post evening or maybe evening tail in the ionosphere. So that's nighttime. Fengyun helps quite a bit cover the polar region. In the E region, we have a lot of data from Fengyun and the cosmic 2 in the equator. This one helps you to do 2 hourly. So we can see I must point out this on left-hand side, I call the TEC. In the paper, when we did the E-region retrieval, we're using this slope in at a 20 and 50-kilometer slope. That's a bottom-up slope, and to infer the vertical TEC. And we did very ad hoc kind of a scaling, just multiply constant. This is a map you get from that TEC. And you can see this is very consistent with F region you just saw, and depletion in the asymmetry and the enhancement afterwards and asymmetry. And now back to the E region, I will just pick a one altitude, 110-kilometer electron density. You don't see much perturbation in the tropical region, but you do see in southern hemisphere, you have quite a bit. This is daytime depletion. And unlike the northern hemisphere in the F region, this is much less kind of sensitive to that storm. At nighttime, E region is very interesting. This is a same thing, proxy for the vertical TEC. You see a little bit enhancement here right at the storm onset. And nighttime at the lower E region, you see enhancement, short enhancement. This is associated with the precipitation electrons, which is associated with the aurora. I'll show you later. And coming from high latitude and expanded to all the way to mid latitude. This is where we hear a lot of report from that. The associated with the electron density also happened to here. Let me see if I bring back my pen. That's better. So this is the nighttime. When you average, I try to make a mosaic, just like the other satellite, low Earth orbit VIIRS day-night band. They make a mosaic all the nighttime and to get an aurora shot on this. From the E region electron density, I can also make a mosaic using all the data together with I would say this is a 9-hourly for the first UTC every day. And I can barely make a global map out of this. And you can see this is E region, the nighttime shows up this arc that's consistent with this aurora. And then lasts for a day maybe, and a little bit decay. So this is where the sighting in I pick up this UTC time just to highlight the US part of night. So that's where a lot of reporting showing the very low latitude aurora. So that's consistent with the report. If you want we want to make a global map, like this is where the same thing, and VIIRS mosaic, and you can see nighttime. I don't have a good coverage, but you sort of see this a little bit arc from the consistent with this aurora, but you expand it from the quiet time. Then later on, you see this is the white spot is a Ukraine, Russian region, but the precipitation electron happen in both day and night. So if I go to daytime, where is it? This is a daytime. I have a much better coverage. In the E region, although I have the aurora from I have a electron density, but from the ionization, but this event so strong, they punch the whole polar region even during the daytime significantly above the ionization part. So you can just ignore all of this outside ionization day. You can see it's a stand out, just look like this aurora, and you can see daytime aurora from the electron density. You can see this one is shrinking a little bit and shrinking further. So daytime coverage is pretty good from this 3 satellite combo.
I'm afraid we've reached the time.
Yeah. Oh, sorry. I would just quickly run over to this is a daytime polar region ionosphere. Yeah, I'm getting to that point. So get to my recommendation that I mentioned that this storm is it's a pretty interesting to the E region, F region, and we have a coverage on that. And we see the asymmetry in the hemisphere responses, and we find it's extended to the low latitude, very consistent or report. Come to the recommendation. I really suggest not for the provider, the LO provider, not to QC the L1 data, level 1 data, because I find a lot of useful stuff. Probably you don't feel interesting. And also I like to recommend increasing more this pot limb sounding, which is below horizon, and increasing the top of the RO data. So with that, I'd like to thank all the data provider and the support from NASA. Thank you.
Thank you. Yeah, I think we have a quick question.
Thank you. That's Christian Marquardt. A very interesting talk. I have a question and a comment. On the question, you have been showing data around, around 100 kilometer up to 300 kilometer. Have you considered using GRASS data? Because since a while we are taking ionospheric measurements up to 300 kilometer.
Yes,
And the
I noticed that. I appreciate it very much. That way, I'm studying those high scanning data, and I'm trying to do the more retrieval to cover the low E region.
Okay, that would be great. The comment is, there was a talk last week by Maria Para-Ortega, and she showed that from the Ukraine interference, we both get reduced numbers of occultations coming out of several RO receivers, not only Spire. And yeah, it's true, we also have increased data rejection rates, but it's not only that, I mean, from the quality control, but it's also that in parts the receivers do not seem to be able to actually track occultations at all. So it's not only the data providers who are responsible for the data gap there.
Yes, it's my this is a private communication with Aspire and Planet IQ. I believe they are still tracking the data. They just at the level 1, before the level 1 processing, they kind of kick out those data.
Okay, in GRASS and Sentinel-6, there are lower numbers probably. But anyway, we can discuss that.
Yeah.
In that way. Thank you.
Thank you very much. Our next speaker is Riccardo Notar Pietro from UMetSat.